This is video help for problem 15.4. Now 15.4 looks exactly the same in the two editions, except there was a word changed in part D. It was the word double in the old edition was changed to have in the new, and don't do that. Go back and use double, and I'll explain in a moment. Here's our basic signal to noise ratio per voxel. We've got ourselves, all the stuff that depends upon the number of protons that are and what they're doing and everything, and the coils and all that. We'll assume we can't change that we certainly can't change our protons. But what we can change is the volume, the voxel volume, over which we're going to analyze, and the signal we're going to analyze, and the noise, which depends upon remember the square root variance and all that. The bandwidth, that comes because the noise is proportional to the frequency range, but per voxel, divided by nx times ny times nz, the noise per voxel. So we can change these. These are imaging parameters. And in part A, you imagine that you're only changing the read parameters. Forget delta y, delta z, ny, nz, and just keep delta x, bw, and nx, and that's that. So in part B, we're going to have a look at, just checking actually answers given to us, actually in B and C, in table 15.1. And in doing so, we're going to calculate the bandwidth per voxel. That's just BW divided by NX, because remember, we forget NY and NZ. The voxel signal, that's proportional to the volume. See, this volume, it's just the volume, the signal is going to go up by the number of protons we've got in there, the density, times the volume. And the field of view we can change. Lx is, the number of sampling points times our delta x resolution. That is, we have delta kx equals 1 over Lx, and that, of course, goes back to other things we can change. We can't change gamma bar, but we can change the gradient, and we can change the bandwidth. Delta t is 1 over the bandwidth. So you can solve for bandwidth over nx from this, and you just get gamma bar gx delta x. And these, you just start cranking away and seeing how things change. In these tables and everything we're talking about now, we're always just looking for factors of 2 or 1. We're imagining doubling something or taking half of it. We don't, sort of go in between, like 1 over the square root of 2 on one thing and 1 over the square root of 2 on another thing to make a 1/2. So this is our simple little scheme here. And that's why we choose the simple examples we have. Part C is just like in B. You're just cranking along here. Remember, by the way, the total sampling time is nx delta t. That'll come in part E. And the final answers you can check. There's a couple columns of answers corresponding to these things that are not there, but the initial columns and the final columns you'll be able to check yourself really easily. Now in part D, take delta x to go to twice the original delta x. I should say delta x equal to delta x 0, where delta x 0 is the initial one that we had. I should have done that every time I talk. Well, in the old edition, we had double and use the old edition. If you use half, the only way you'd be able to do something different is you'd have to do some square root of 2's and things like that. So what we're doing, you see, is looking at the two cases that if you looked at cases 6, 7, 8, 9, and then you compared it to cases 4, 5, you'd ask yourself, well, gee, I should look at the case, the parallel case where you'd double the field of view and keep n fixed, as opposed to taking half of n and fixing L0. So now it's just like B. And you'll see there are two obvious choices. You know, if you've got yourself, going back to our original expressions involving gx delta t, and if I'm doubling Lx, then I must have to have gx or have delta t. Those are my two obvious choices. And then the two cases follow. Once you do that with this choice and half of that or half of that, everything else is fixed, and you'll get everything else. Finally, in part E, you can quickly calculate delta x0, from the original, we're given field view, we're given nx, and you can calculate the signal to noise ratio per voxel. By the way, what you can do in the signal to noise per voxel is you just go back to the original expression, delta x over the square root of bw over nx, put in bw over nx equals gamma bar gx delta x, and you can just quickly see that the signal to noise per voxel is just that. Well, you calculate delta x, you know gx, you know gamma bar, you'll get an answer. Now suppose you want to reduce this by 1/2. Your signal to noise would go down. Could we minimize gx? Could we change gx to try to make up for it? Well, gx is 1 over gamma bar delta t Lx. You can, by the way, we're given ts, so you can replace delta t by ts over nx. Remember, sampling time, total number of steps times the time step. And you can look at this and say, oh, well, what's the minimum value I can have here? Well, ts cannot be bigger than t2 star. Therefore, 1 over ts cannot be smaller than this value with t2 star stuck in for ts. And that'll give you a minimum value. And you can compare it. And you'll find that you don't get very much difference, very much improvement trying to go to this minimum value compared to the original GS.